But of course, as you pointed out last time, what's the big Achilles heel of method by exhaustion or method of exhaustion?
It doesn't really work for infinite domains.
It doesn't work for infinite domains at all, right? Method of exhaustion requires us to go through and check every element. So if the domain is infinite or the set is infinite, we're going to be here for a while, right? This is supposed to be like a 3-hour credit class. This is a 3 credit hour class. So the point is, I wonder, like, how many could we get through? If we're trying to prove the integers were a subset of the rational numbers, and we had the rest of class, not only today, but Thursday, and then when we get back from Thanksgiving break, all of those classes, how far do you think we can get by method of exhaustion? 50,000 maybe? I think I could prove every integer from 1 to 50,000 would be in the rational numbers by December.
I don't want to.
Yeah, right. It's a bad thing to do, right? Exactly. So instead, let's move on to a much better method. And that's the exact same thing we did before, right? When we had infinite domains before, we couldn't do anything. What do we say? Let's use something like direct proof, right? So let me introduce 2 sets to you. They're both my friends. And that is 2z. And 2z equals every element of the form 2k, where k is in z, aka multiples of 2. And 4z equals every element of the form 4 times k, where k is in z. And again, you could write these guys in our other set notation, or you could say m in z such that m equals 4k for some k and z. You do if you want to. I think this is easier. It makes more sense. So yeah, these are my friends, 2z and 4z. Here's the question. What's their relationship?
2z is in 4z. No, backwards. 4z is
Yeah.
in 2z.
It might look like that, right? The weird thing is that 2 is less than or equal to 4. So you might think that 2z's and 4z just kind of just not think about it a lot. But then when you think about it for 2 more seconds, like Toru did, you see, oh wait, 2 less than 4 is the exact reason why 2z contains 4z. Because if you think about it, you get multiples of 2 every 2 numbers, but you don't get multiples of 4 until every 4 numbers, right? So that is why 2z is contained in 4z, because we're saying that every multiple of 4 is a multiple of 2. So what this would be saying is that for all n in 4z, n's in 2z. It's now these are infinite sets, right? There's infinitely many multiples of 2, infinitely many multiples of 4. Method of exhaustion is going to fail. So what's a boy to do? That's a real question. What is this boy to do?
I guess make 4k into 2 times 2k or something like that.
Yeah, exactly, Toru. The brilliant part of that, more than what you said after the 2k, 4k thing, is using k. The brilliant part is prove it in general, right? Instead of using method of exhaustion to prove each individual element, right? Instead, look at a general element of 4z and prove it must be in 2z, right? Prove that the property of being in 4z logically means it also has the property of being in 2z. Right, that's the idea of direct proof. That's the generalization. That's what allows us to do it. So proof, we're gonna let n be any arbitrary / particular element of 4z. We want to show that n is also in 2z. That's what we're trying to do. So here's where we're going to do it. note, by definition, since n is in for z, there exists a k in z such that n equals 4k. And then coming up next is exactly what Tori was talking about. If you're a multiple of 4, you're definitely a multiple of 2, right? Why? Because 4 itself was a multiple of 2. So very like that. N equals 2 times 2k. Well, clearly from this, as long as 2k is an integer, this would be a multiple of 2. So we have a little something to prove here. I'll say recall since 2 is in z and k is in z, and z is closed under multiplication. Because of all that, 2k is in z. Thus, actually, I feel like saying therefore. I feel like a therefore here. I don't know why. It feels important. Therefore, n, which equals 2 times 2k, is in 2z by definition of 2z. And then hence, because we showed that any element, old element in 4z is going to have the property that can be written as 4k, n equals 4k, which because the property can be written as n equals 2 times 2k, which is the property of being in 2z. Any old element in 4z is in 2z, which is exactly what it means for 4z to be a subset of 2z. Oh, square thing. Boom, done. Any questions? Good, I hope this makes sense, right? I mean, really, this right here is a universal statement. And all we did is a direct proof of universal statement. This is just chapter 4. This is really not anything new. As I keep saying, like, what we've done is we've kind of left proofs behind, and now we're using proofs to prove things. And so we're using proofs to prove things about sets right now. So no new proof techniques happening here. I mean, direct proofs might seem hard in the beginning, but look how easy they are now. Like now this feels like weak sauce. This feels like the proof is the easy part here. Another example. I'm trying to get rid of some of these definitions just to give us some room here. Let's go ahead and let S equal this weird, interesting set. It's going to be P and N such that P is prime and P is greater than or equal to 3. So that's S. S instead of all primes is greater than or equal to 3. We're going to define T to be all n in the natural numbers such that n is odd. Or another way to write that would be every element of the form 2k plus 1 such that k is in T. And by the way, you might think like, oh, this is the more formal definition than this, because look, this looks more numbery and more mathy. But this is totally fine, because we've defined what being odd means, right? Odd means you can be written as 2k plus 1. So like because we have that, because before we define what odd means, this is a totally formal, rigorous, nice mathematical definition. Nothing wrong with it at all. Same thing here. All right, so here's the claim. I think you guys know where this is going. If not, maybe you didn't think about where it was going, you just lived in the moment, which is I commend you for that. But anyway, the claim is that S is a subset of T. The claim being that the set of primes greater than or equal to 3 is a subset of the odd numbers. And again, primes are infinite, numbers are infinite. So we're dealing with infinite domains here. So method of exhaustion is a no-go. Let's go with direct proof instead. Or I'm sorry, we call it the element method instead. So proof. The proof goes like this. Of course, we start off with let P be any arbitrary / particular element of S. And so starting from a P being any arbitrary element of S, we want to show that any general arbitrary element of S must be in T. That's how we show that every element of S is in T, which shows that S is a subset of T. So here we want to, it feels like I'm saying the same thing over and over again, but they're slightly different. So we want to show that P is also in T. So first things first. P being an element of S, that means we know since P is an S, by definition, P is prime and P is greater than or equal to 3. By the way, let's take a moment to admire how this and symbol right here, at the beginning of the year, it's probably a thing you'd have memorized, maybe and or you got confused, a lot of stuff like that. Now it's second nature. I bet no one out there saw that and was like, what's that mean again? You probably didn't even realize that I wrote a caret instead of the word and. Like that's ingrained in their brains now. Isn't that great how we've learned? It's awesome. The weird thing about a class like this is that if you make it to the end of the class, you might not know all the material up to the end of the class really that well, but you're gonna damn sure know like the first half of it really well because that gets used over and over and over again. And it starts at the back half, just to practice the first half. But anyway, so we have that P is a prime and P is greater than or equal to 3, and we want to show it has to be odd. That's why we show it's in T. That's why we show S is subset of T. So, why? Why must a prime greater than or equal to 3 be odd? Like what's the intuition? What do you guys think? I mean, we kind of know this, right? Like we know that 2 is the only even prime, meaning any prime bigger than 2, aka greater than or equal to 3, is going to be odd. We think about that, right? Like even numbers look very not prime to us. They look very composite. Why?
Because they can be divided by 2,
Which
which is
Exactly,
not 1 or
right?
itself, right? Yeah.
Exactly. They can be divided by 2, which 2 can be divided by 2, but the thing that makes 2 special is the fact that 2 is 2, right? If 2 divides anything that's not 2, then that makes 2 a non-trivial divisor of that number, meaning that number is not prime. It's in fact composite because it can be divided into 2 and something else. So here's our aside. We should note if P is greater than or equal to 3, 2 is a trivial divisor, or if P is greater than or equal to 3 and even, then 2 is a trivial divisor for P. And remember, a trivial divisor is just a divisor for P. It's not one or itself. A positive divisor. It's not one or itself. So P is greater than or equal to 3 and even, then 2 is a trivial divisor for P. Thus, P is not prime. So we have a little work to show it's not a trivial divisor. show it to, obviously it's a divisor. To show that it's a trivial divisor, right? It is. It's not. It's not. It is. Show that 2 is a trivial divisor. All I have to do is show that p is not 2, which clearly it's not because it's greater than or equal to 3. So it looks like here, this is kind of our proof, but it looks backwards, right? We're starting with if p is even. We're showing that if p is even, then it can't be prime. So what did we just do? This is a proof by contradiction, essentially, right? Because we know p is prime. And so if we further assume that p is even, and since it's greater than or equal to 3, we can show that p must not be prime, but it is prime. So this is a contradiction, right? Assuming p is even does not work with p being prime and greater than or equal to 3. It's going to lead to a contradiction, which will mean that p can't be even. It must be odd. Which is exactly what I want to show. But boy, it's just a nice little contradiction proof. I feel like it makes more sense if you don't really think about it. But anyways, so this is the problem, right? If p were to be even, then it would not be prime. But p is prime, so that means it can't be even. That's the idea. That's what we're going to capture here. So let's say, assume for sake of contradiction that p is even. Then, by definition, p equals 2t for some t in C. So it means to be even. Thus, 2 divides p. And then I'll say, note that 1 is less than 2, which is less than 3, which is less than or equal to p. Hence, 1 is less than 2, which is less than p. Therefore, 2 is a non-trivial divisor of p, so p is not prime. Contradiction. Does that make sense? Non-trivial divisor is a divisor that's not itself or 1, and it's positive. So it's a divisor greater than 1 but less than itself. So choose a non-trivial divisor of p, so p is not prime. That's a contradiction. P cannot simultaneously be prime and not prime. Hence, our assumption that p is even must be false. And if p is not even, I've proven before that if you're not even, you're odd. Thus, p is odd. Meaning p is in t by definition of t. And then I'm going to throw an ergo out there because I've already used therefore. Ergo, don't use ergo outside of my class. People don't like it, but I think it's fun. T, ergo, as a subset of t, right? That was the whole point of all this. We've proven that if p is in S, it's a prime greater than or equal to 3, meaning It can't be even because that would make it not a prime. So therefore, it has to be odd, which is exactly what it means to be in T. So if P has the property that's in S, it's going to have the property that's in T. Therefore, it has to be subset of T. Oh, ooh, ooh. Box. There go monkey noises. That's the box. We're done. Well, for this proof. Any questions?
Yeah. For the two different sets, so like when we first start this proof,
Mhm.
I mean, I can intuitively tell that the reason why the infinite set of primes is smaller than the infinite set of odd numbers is because there's more odd numbers. But is there any, like, do we just assume sets? Like, is there like some intuitive trick that we can use when sets aren't so obvious? Like, because sometimes it may not be so obvious that one set's actually infinitely bigger than the other one. You know what I'm saying?
Well, that's kind of what the proof's for, right? In a certain sense, well, bigger is a weird word, right? Because they're both infinite. So what's it mean to be bigger? We'll talk about that later. In a certain sense, S and T are actually going to be the same size. They're both going to be the same size as the integers in a weird way. It's called countability. I love it. It's awesome. We'll get to it. But the point is, so is T bigger than S? Hard to tell. And the reason I say that, I'll just give you guys a really quick example. Like, you can ask the question, are there more integers than even numbers? And at first glance, you might think yes, because you have 0, 1, 2, 3, 4, 5, not 6, -1, -2, -3, -4, -5. So we have all of these guys are integers. But if you look at the odd numbers, my head will block it. If you look at the, there we go. If you look at the odd numbers, or I'm sorry, look at the even numbers, you have 0, you don't have 1, you have 2, you don't have 3, you have 4, you don't have 5, you don't have -1, but you have -2, you don't have -3, you have -4. Like that, right? So it looks like there's infinitely more. Wait, I'll go down. That's what I'm doing. There you go. So it looks like there's infinitely more integers than even numbers because you're going to have all the odd numbers. But here's another way to look at it. Imagine pairing up 0 with 0, -1 and -2, -2 and -4, 1 with 2, 2 with 4, -4 is going to go, or -3 is going to go to -6, 3 is going to go to 6, -4 is going to go to -8, -5, -10, out like that. Well, then you see that the even numbers aren't really so much like half of the integers, but just a stretched out version of them, right? Like if you take the integers and you stretch them out by a factor of 2 and put them back on the number line, well, you land on all the even numbers. And so, well, in that sense, there's not really more integers than even numbers. It's just the even numbers are stretched out. It's like if you take a rubber band, I have one. If you take a rubber band, you stretch it. There's not more material now. It's just, or less material. It's just stretched. Anyway, we're gonna have whole classes on that. But for now, the point is this whole idea of there's more odd numbers here, so S is gonna be less than that. It's kind of not necessarily a good way to look at in terms of the amount of numbers. The better thing to look at is just almost the structure. Like, does the structure of the odd numbers contain the structure of the primes greater than or equal to 3? And it does. And the way you can wrap your mind around that is the proof itself. Like the proof, like this, the proof that S is a subset of T is the proof that, in a certain sense, S is inside T. Maybe we should really be talking about sets being inside sets versus sets being bigger than sets, because it gets kind of weird. But I'm sorry, am I answering your question, Herman?
Yeah, that answers it. if we were to start out trying to prove the opposite, would we get weirdness in the proof?
Yeah, absolutely. Well, actually, Herman, I'm glad you said that because that brings up our next topic, which is disproving things or disproving containment. We'll talk about that right now.